For the past few months, I've been working on this. It is the bubble inflation test, which I've been using for my bachelor thesis to characterize the mechanical behavior of the material Ecoflex 30, since it is a popularly used material within soft robotics, in particular for inflatable soft robots. However, characterizing materials such as Ecoflex comes with a few difficulties. First of all, it is an elastomer, known for their inherently nonlinear elastic behavior. So the well-known Hooke's law that applies for many other materials with linear elastic behavior doesn't apply for them. Elastomers typically exhibit hyperelastic behavior, meaning that it's capable of making large deformations while returning back to its original configuration once unloaded again, ideally being completely reversible. However, most elastomers also exhibit some form of viscoelastic behavior, where energy is partially dissipated within the material's internal movements, making it irreversible. These effects are time or cycle dependent, making the predictability of such materials only more complex. The final goal of my research was to find a material model that describes this mechanical behavior of Ecoflex 30. I focused mainly on the hyperelastic characteristics, since I was able to minimize the viscous phenomena, which I will explain later on in the video. For this, I used the bubble inflation test, and you might be asking, but why are you using a bubble inflation? What? Let me explain. A bubble inflation setup consists of an inflation platform, where a film of material is clamped between the platform and a circular rim at the top. Air is then supplied through the platform, which causes the film to inflate into a spherical shape, the bubble. Since the clamping conditions are rotationally symmetric, the stress concentrations within the material are minimized during deformation, in contrast to... Therefore, this method is able to reach larger deformation ranges, making it ideal for biaxial loading of hyperelastic materials such as Ecoflex 30. How this method provides the required material characteristics, I'll explain later on in the video. To fabricate a bubble inflation setup for myself, I walked through the following process, where I started with the design of my inflation platform. It obviously consists of a platform, where a connection piece for air supply is implemented. Thereafter, a rim is made to be put on top. These clamps were available in the lab, so I made some indentations where the clamps could fit into, at the bottom of the platform and at the top of the rim. This is to ensure minimal difference in clamping conditions between samples. I had some similar film of material laying around, so I clamped it in between the platform and the rim to test if the setup actually worked, but as you can see, there's only some leakage. With an O-ring I found in the workshop, I was able to minimize this problem by adding it onto the clamped film. And as you can see, it works a lot better than before, as the bubble does not immediately deflate during inflation now. The next step was to fabricate material samples of Ecoflex 30. For who is not familiar with the Ecoflex series, it's a two-component silicone rubber, which you only have to mix in the right proportions to let it cure. Like I did here. After that, I also put it in this vacuum chamber to remove most of the air out of the liquid, to achieve a mostly homogeneous material. I then used a syringe to measure and pour the mixture into multiple petri dishes, whereafter I let them cure overnight. The next day, I put the material sample to the test, and as you can see, the sample fits the clamping platform nicely. What was even better though was the fact that the material adheres quite well to the surface of the platform, reducing the leakage even more. Now the inflation platform worked for the Ecoflex sample as well, it was time to make an inflation system that could also reliably inflate the upcoming material samples. To achieve this, I used a syringe pump for the supply of pressure to the system, for which I know the volume displaced by the plunger. However, I also want to know the pressure of the system during inflation. So, a pressure sensor is added to the system as well, resulting in this. But how is the syringe pump driven? A stepper motor. But how do you control the stepper motor? Electronics. Oh fuck. Before I started with my bachelor assignment, I didn't have a lot of experience with this. But now, I still don't. However, I did manage to get this shit working. Okay, let me explain. The stepper motor rotates for a number of steps, which corresponds with a rotation of the shaft and thus a translation of the plunger to displace the air. The stepper motor knows this because I say so on my laptop, which is connected to an Arduino, which is then connected to the motor. You don't want to know how long this took me. Back to the inflation setup. It works now, but what am I going to do with this shit? Well, let me explain. And now comes the technical part, which actually came before the making process of this thing, but wouldn't make a lot of sense if I told you in the beginning, so I'm telling you just now. As I stated in the beginning, the goal is to find the material parameters of the mechanical behavior, and these can be found using the geometry of the bubble and the internal pressure of the system, since the amount of pressure required to deform the material to a certain point tells something about the stiffness of the material in that loading configuration. I won't get into the details, but here's a short summary. The change in the volume by the syringe pump causes an increase in pressure, idle gas law, since it's assumed that the temperature is constant and no leakage occurs. This pressure is then measured by the sensor, for which is assumed that it's equal to that throughout the whole system. Since the walls of the system are assumed to be infinitely stiff, the only part of the system that's then able to deform is the material film, for which the stiffness is finite. The pressure increase therefore causes the film of material to inflate like a bubble. The bubble is assumed to be shaped equal to that of a spherical cap, because I want symmetry. Why? Well, because the stretch of the material will be determined at the apex, for which the stiffness is then equal in the two tangential directions, making my life a whole lot easier. The stretch and thickness is then determined by using the incompressibility and uniform thickness assumption, which can be related to the tangential stretch, by guess what? Also the incompressibility assumption. The stress is then calculated using the hoop stress, with the pressure and the geometric variables known. Oh fuck. A measurement system for the geometric variables of the bubble. I completely forgot about that. At first, I wanted to make a simple mechanical system, where I would measure the height of the bubble with a caliper from above. But for multiple measurements, this would be really tedious and sensitive to error. So, therefore, I went for the computer vision approach. And this is where it got a little bit messy, because I still didn't know shit. I started with the height measurements from above, first with Aruka markers and later on also with checkerboards. It uses the increase in square size when approaching the camera to obtain the height of the bubble over time. And that went pretty... So, after that I went to make the logical choice to measure the bubble from the side, like what a sane person would do. I calibrated the camera using a checkerboard, whereafter I filmed the bubble inflation with the same camera parameters at the same position to obtain footage like this. The video could then be image processed per frame, which I did like the pro. I'm not a pro. I mean, it's ugly, but it works, and yeah, it works. It just works. Eventually, for each frame, I could obtain a binary image of the contour of the bubble. Now, I only had to find a radius and the height of this contour. Easy, right? Nope, this took me so freaking long. I had to find a way to fit a circle onto this contour image. But for some reason, it would just give me everything but a right fit. Like, what the fuck is this? Like, the whole curve is there and it just does... What? I didn't know why. I just tried a lot of different things until, luckily for me, something like a week before the deadline, it started working. Like, thank God, looking like this. Oh. Now, with the radius and the height known in pixels, I could translate it to physical dimensions using the resolution I got from the checkerboard calibration, which I needed to find the stress and the stretch of the bubble during inflation, meaning I finally have everything I need. The last part of my research was to combine all this gathered data to obtain the material parameters of Ecoflex 30, my end goal. First of all, the experimental data was used to find the stress-stretch relation of Ecoflex 30 under bubble inflation, which is shown in the curve here. This graph already shows how the applied force is related to the deformation of Ecoflex 30. However, this is not a material model of the mechanical behavior yet. For this, I have used the so-called strain energy function of the Gent material model, which describes the behavior of hyperelastic materials based on the stretch ratio and some material parameters in a standardized equation. A relation for the stress can be derived from this strain energy function, enabling me to graph the material model against the experimental data. The goal here is to find a material model that follows the experimental results closely, to achieve an accurate model. For this, the material parameters are optimized to achieve a minimal error between the experimental graph and the material model graph, resulting in this. The one graph that describes my whole research, the hyperelastic mechanical behavior of Ecoflex 30. Note that I'm saying hyperelastic behavior since I neglected the viscous behaviors. Remember? Because of this. It says, with the use of low strain rates, a pre-stretch and initial cyclic loading up to the maximum stretch, the Mullins effect, hysteresis and other viscous behavior is minimized, such that only the hyperelastic behavior is dominant during inflation. The results are therefore limited by the conditions the material is tested under. Besides that I've only been able to analyze one material sample, which makes it all quite unreliable. However, I do think it may serve as a good indication for the actual material behavior, and provide an approach of using the bubble inflation test to characterize hyperelastic materials. In case you are interested in this topic, I've put some sources in the description. And hereby I conclude this video about my bachelor thesis. Hopefully you enjoyed watching and learned something new. Let me know what you think of it. See ya!